When we write chemical equations, we can write them in molecular form, which is probably the most familiar form, where we see the whole formula for the ionic or the molecular substance for the reactants and the products. Now, ionic substances, many of them, not all, but many of them, are water soluble. And so when ionic substances that are water soluble are written out, we need to remember that they will dissociate. Those ions will come apart and be free floating and independent of one another. So in reality, what we might write as, say, NaCl for sodium chloride isn't floating around in little, pairs of sodium and chloride ions, connected to each other. They're independent sodium ions, independent chloride ions, and water surrounding those ions is what carries them off, and they are spread uniformly throughout the homogeneous solution. And so what you see is a representation, a reminder of our solubility rules. Again, first and foremost, alkali metal compounds and ammonium compounds are always soluble. You see, you work your way down through the list, then the rest are based on the anions that would be present, and we can use these to help us to understand the true nature of the chemicals that are involved in our reactions that we express with an equation. So the first step is to write what's called an ionic equation, and this is going to represent those water-soluble substances in their true state. So the first thing to determine is by looking at a molecular formula, which is by and large the most common type of chemical equation that we see, what should stay written in molecular form and what's going to get dissociated into ionic form. Well, again, water-soluble ionic substances, the biggest clue there is that they have AQ written as the state after them. If they're ionic substances, again, you can consult with the solubility rules just to verify that, in fact, they are water-soluble. Things that are considered to be strong acids, you had 3 strong binary acids and then a handful of strong ternary acids. Those will be written in ionic form. And then likewise strong bases, okay, your alkali metal, alkaline earth metal bases. Things that will remain in molecular form, things that are insoluble, so if there is an S written after the formula, then you know it's a precipitate, and so it's going to be in that whole molecular form. Acids and bases that are considered weak, that would only partially dissociate, will remain in molecular form. And anything that is a gas or a liquid in its natural state will be listed with a G or an L. Those stay in molecular form as well. So if we take a look at this example, lithium carbonate plus manganese 2 chloride yielding 2 lithium chloride plus manganese 2 carbonate. And so as we look across at these formulas, we can use those states as a clue. The first one we see lithium carbonate, it says aqueous. And lithium is an alkali metal, so we know that's definitely going to be water soluble, so that formula will dissociate. Manganese 2 chloride, again, is written as aqueous. Manganese is not an alkali metal, but chlorides, for the most part, are soluble. There are some exceptions, but manganese is not one of them. So it, too, will be written in dissociated form. All right, and so you can see as we break these down, based on the stoichiometry of the ratios, we have 2 lithium ions for every 1 carbonate. Remember, the 3 is part of carbonate's formula. And so you can see that written here in purple. Manganese 2 chloride, it takes 2 chloride ions to offset the charge of the manganese 2. So you have Mn2 plus aqueous plus 2 chloride aqueous. Note, all ions are always in the aqueous state. Then we look to the product side. We have 2 lithium chloride aqueous. Again, it's an alkali metal compound, and it has the aqueous symbol there, so we're going to split that. It's going to dissociate. And here we want to be careful because every lithium chloride will give us 1 lithium ion, 1 chloride ion. But there's 2 lithium chlorides, so we need to distribute that amongst both of those ions. And finally, our last one here, manganese 2 carbonate, we see it's a solid, so solids remain in their undissociated state and therefore stays in the molecular form. Now, when we look at our ionic form here, we might notice that there are ions that show up on both sides. For instance, the lithium ions, all right, the Li plus, and there's 2 of them on each side, as well as the chlorides, 2 chloride ions on each side. These are what we call spectator ions. All right, and spectator ions are just that. They're spectating, they're watching. They're not actually involved in the overall true chemical change that's occurring. So what we can do is we can eliminate those, we can cancel those, and what we get is called the net ionic equation. It's showing us the net effect of what's happening. In this case, the manganese 2 ions combining with the carbonate ions in solution to form the insoluble precipitate manganese 2 carbonate. And so this right here is what we would represent as our net ionic equation. It's a scaled down, trimmed down version of the ionic equation. So when we write net ionic equations, okay, the first is to write the balance complete the balanced molecular equation, and then write the ionic substances in ion form. Now, one strategy is to put that into brackets, and I'll explain and show you here in just a minute why that is. And then you put the coefficients outside the brackets. Then you write the total ionic equation. So you get rid of your brackets by distributing, just like we would in algebra when you have coefficients. Identify and eliminate your spectators, and then consolidate the remaining species. Make sure that the final equation is balanced, both atom-wise and charge-wise, and that the coefficients are in simplest form. That's probably an important afterthought, but one that you don't want to forget. So if we have silver nitrate plus magnesium chloride, we do a double displacement reaction there. We're going to get silver chloride solid plus magnesium nitrate. And so if we start by writing this and looking at which of these formulas are going to dissociate, silver nitrate is soluble. And so, well, first we're going to balance it, excuse me. So if we balance it, we need a 2 in front of the silver nitrate, a 2 in front of the silver chloride. That balances the nitrates and the chlorides. Now that we have the balanced molecular equation, now we can begin to break down those ionic species. And so silver nitrate is soluble. So what we're going to do is we're going to say we're going to put a 2 on the outside of the brackets. And then inside the brackets, 1 silver nitrate is going to give us 1 silver ion and 1 nitrate ion. Okay. Magnesium chloride, likewise, okay, is going to break down into, it's going to dissociate into magnesium 2 ions and 2 chloride ions, right? Product side did the same thing. Our silver chloride is molecular because it's a solid, and then magnesium nitrate, we're going to break that down inside the brackets, okay, showing that 1 unit of magnesium nitrate is made up of 1 magnesium ion and 2 nitrate ions. Now, next thing we want to do to get the total ionic equation is to multiply through, get rid of the brackets. So that means we're going to have 2 Ag plus ions plus 2 nitrate ions plus, right, there's no coefficient to distribute, so we just keep what's inside the brackets, Mg2 plus and 2 Cl minus, yielding 2 AgCl plus Mg2 plus 2 NO3 minus. Okay. Now looking at this, we see that the nitrates are on both sides, as well as the magnesium ions. So those are going to be factored out. Those are spectator ions. And so then if we consolidate, we have 2 Ag plus 2 Cl minus, yielding 2 AgCl solid. Notice they all have a coefficient of 2, which means they can be reduced. And we get Ag plus aqueous plus Cl minus aqueous, yielding AgCl solid. And that will be our net ionic equation. Next example here, you follow the same process. We have iron 3 chloride plus sodium hydroxide. And so if we first do a double displacement, we're going to get iron 3 hydroxide solid plus sodium chloride aqueous. All right, going through and balancing the molecular equation, we're going to need a couple of 3 coefficients. And so now when we break these down, FeCl3, okay, that's going to break into or dissociate into 1 iron 3 ion and 3 chloride ions. Sodium hydroxide will dissociate into sodium ion and hydroxide ion. There are 3 sodium hydroxides, so we need to put the 3 outside of the brackets. On the product side, we've got our iron 3 hydroxide solid, and our sodium chloride dissociates into sodium ions and chloride ions. But again, there's 3 NaCl, so we have to put a 3 on the outside of the brackets. Eliminating the brackets then gives us Fe3 plus 3Cl minus plus 3 Na plus 3 OH minus. All of that yielding FeOH3 solid plus 3 Na plus aqueous plus 3 chloride aqueous. And again, we can notice that the chlorides are spectating. They appear on both sides, and so they will be eliminated. Sodiums appear on both sides, so they will be eliminated. Those are both spectators. Quick point, doesn't have to be the exact same number of each of those species. You can do partial canceling, like if you had 2 on one side and 3 on the other. 2 of them would cancel, but 1 would remain. But that's something that we'll see happen in future instances of net ionic equations. All right, getting back to this one, we consolidate everything, and if we look at the coefficients can't be reduced, so it would simply be Fe3 plus aqueous plus 3 OH minus aqueous, yielding FeOH3 solid. All right, in our last example here in the practice, looking at chromium 2 nitrate and copper 2 sulfate reacting together, we can see we already have the balanced equation given to us. There's a few more formulas here, but it doesn't make anything more complicated. It just means that you've got more formulas to analyze. Are they dissociating or not? So the chromium nitrate, okay, if we break that down, now here we've gotten away from showing the brackets. That can be used as a tool to help you with that breaking down. But if you're getting comfortable looking at the formulas and knowing that you have to distribute the coefficients, you can go right to the total ionic equation. So again, whatever you're comfortable with. So if you've got 6 chromium 2 nitrates, what that means is that you're going to end up with 6 chromium 2 ions. There's 2 nitrogen or 2 nitrates times 6. That's going to give you your 12 nitrate ions. Okay. And again, all ions should be aqueous. I don't have it written here, but they should be AQ with that. All right, 3 copper 2 sulfates, again, aqueous, so you're going to get 3 copper ions, copper 2 ions, and 3 sulfate ions. Over here we have copper solid, so that's written in molecular form. And we have chromium 3 nitrate, and there's 4 of them, so you're going to get 4 chromium 3 ions, and you've got 4 times 3, which is 12 nitrate ions. Then our final product is chromium 3 sulfate, and so you're going to have 2, okay, because we've got the subscript 2 here, 2 chromium 3 ions and 3 sulfate ions. Now looking at this, we can see that we have in common nitrate ions, 12 on each side, so they're going to be spectators and will be eliminated. And we can also see that we have 3 sulfate ions on both sides, so they are spectators and they will be eliminated. Okay. Now, as far as anything else, we see chromium on both sides, but they're not the same species of chromium. On the reactant side, we have chromium 2s. On the product side, we have chromium 3s. And notice that there are 2 separate instances of chromium 3. So those we can consolidate, but we can't cancel them because they're not exactly the same, charge and atom-wise. Same thing for the coppers. We've got copper on both sides, but over here it's copper with a +2. Here it's neutral elemental copper. Okay, so we can consolidate the Cr3 pluses to give us 6 of those total. And we notice that our coefficients are all divisible by 3. So if we reduce, we get 2 Cr plus 2, yielding Cu plus 2 aqueous, yields Cu solid plus 2 Cr3 plus. And that would be our net ionic equation.